continuing in our discussion of section 2.5. Here is an example of a function which is the square root of 4 minus x squared, and this is a semicircle, and you've seen this 100 times, so you're very familiar with this function. Okay, and we know that the domain is from -2 to 2. And just by tracing the graph, let's trace the graph. Okay, start at 0, and it rises up to 2 and goes back to 0 without any gap or jump. So we see that this function is continuous at every point in the domain, from the endpoints in the interior and into the right endpoint. Okay, example 3. This function, all right, let's go ahead and trace it. We start at 0 and oops, it jumped and then carried on to 1. Okay, so this has a jump discontinuity at x equal to 0. And let's see why that's the case. The limit of u of x, as x approaches 0 coming from the right, is 1, and the limit of u of x, as x approaches 0 coming from the left, is of course 0. And since these two-sided limits are not equal, we know that the limit, or we conclude that the limit of u of x as x approaches 0 does not exist. So when the limit does not exist, automatically u of x is not continuous. But only it's not continuous at x equal to 0. So what did we find out from all those examples that we had? The function, first of all, has to exist at the point that we're looking at its continuity. So let's say at x equal to c, f of c must exist. And moreover, the limit as x approaches c also exists. And the most important thing is number 3. The limit and the function value, they have to coincide. They have to be equal to each other. So that way there's no gap, there's no hole, there's no jump. Here is the greatest integer function. And look at, we see where the points where it's discontinuous. Okay, because there's always a jump at every integer. See that? Jump, walk, jump, jump, etc. So it is right continuous but not left continuous at every integer point. Now why is it right continuous at every integer point? Well, let's take the limit. Let's go ahead and take the limit. Let's just take, say, how about at x equal to 3? I mean, you could take any integer, but I'm just curious. Say at x equal to 3. What is the limit of y of x? Let's just say y of x. As x approaches 3, coming from the right. Well, coming from the right, we see that the limit is 3. And then, what is y of 3? Well, the greatest integer less than or equal to 3 is of course 3 itself. See, these two match. So we see that the limit exists, the function value exists, and they're equal to each other. So it's only right continuous because coming from the right. So it's right continuous at x equal to 3, or any integer for that matter. Now why is it not left continuous? Well, let's take the limit of y of x as x approaches 3 coming from the left. So when you're coming from the left, you're evaluating the greatest integer less than or equal to a number, but since you're coming from the left, it has to be less than 3. So say the greatest integer of, let's just try it, the greatest integer of, say, 2.8. The greatest integer of 2.8 is 2. The greatest integer of 2.9 is 2, etc., etc. Okay, so the greatest integer of a number less than 3 is 2. However, what is y of 3? We know that y of 3 is equal to 3. You see here, they're not equal to each other. Then that's why it's not left continuous at every integer. Now, what is this? You have the famous y equal to 1 over x function, where what is the restriction on the domain? If we write it in interval notation, the domain is from negative infinity up to 0. Okay, union 0 to infinity. In other words, we exclude x equal to 0. Okay, well, let's see. Does it have a limit as x approaches 0 from the right? And then let's take the limit of 1 over x as x approaches 0 coming from the left. Okay, if all my x's approach 0, what happens to the y values? It actually blows up. So from the right, it's plus infinity. From the left, it's negative infinity. So naturally, the limit of 1 over x as x approaches 0 does not exist. Because one goes to plus infinity, the other goes to minus infinity. So we have a discontinuity at x equal to 0. Properties of continuous function. If the function f and g, they are both continuous at x equal to c, then we have the following combinations mean that they're also continuous at x equal to c. So if we add f and g, the sum is continuous, their difference, a constant multiple of a continuous function is continuous. If we take the product of two continuous functions, it is also continuous. What about a quotient? As long as at x equal to c, the function in the denominator is not equal to 0, then we have a continuous function of a quotient. And of course, any n positive integer like x squared, x cubed, etc. And of course, cube root of x, square root of x, provided, of course, that it is defined on an open interval containing c where, this function is defined. Because if we have, let's say, the square root of x, then it's only defined from 0 to plus infinity, and so on and so forth. So what are some common continuous functions? Oh, we've looked at this a lot. Say y is equal to the constant function, like say y is equal to 1, or y is equal to negative 3. These are all horizontal lines passing through whatever the constant value of y is. Okay? What else? Where our identity function, y is equal to x. And of course, quadratic function. Alright? And of course, a combination of those. So let me say we have x squared plus 3x minus 2. Remember, that's a quadratic function, and in college algebra, we've learned how to plot its vertex, so these are continuous functions. In general, any y equal to x to the n and a combination of any of these. Like, that means any polynomial, say y equal to 3x to the 4th minus 2x cubed plus 3x minus 5. That's a combination because we remember any constant multiple of a power of x and their sum is also continuous. Okay, now what else are common functions? Let's see. Let's take a look at our trig functions. Let's try like y is equal to sine of x. That's continuous. Y is equal to the cosine of x. It's continuous. What about y equal to tangent of x? Well, we have to be a little bit careful here because remember, tangent of x is equal to sine x over cosine x. So as long as cosine x is not equal to 0, And when does that happen? As long as x is not equal to n pi over 2, where n is an odd integer. In other words, any odd multiple of pi over 2. Why? Because what is the cosine of pi over 2? 0. What's the cosine of 3 pi over 2? Again, it's 0. And whether you go in the negative direction or positive direction, any odd multiple of pi over 2 is 0. So this is continuous as long as you avoid those critical points. And I'm sure there are other functions like the secant and the cosecant, cotangent, but we just have to be careful. And of course, what about their inverse function? Those are also continuous functions, like the inverse of sine and the inverse of the cosine function. These are continuous functions on their given domain. Okay, but again, like I said, you have to avoid where there's a point where it's not defined, and that means the denominator, if it has a denominator and the denominator is 0, so we exclude that from our domain. Okay, what else? Our root functions, say y is the nth root of x, and what can we use? Say y is equal to the square root of x minus 1. That's a continuous function, but we have to be careful here. First of all, where is it defined? It's defined, and its domain is from 1 on out to plus infinity. So it has a continuity from 1 to infinity, and of course that's got a endpoint continuity because it only has a limit at an endpoint, and it's equal to its function value there, and so on and so forth. I mean, we could take as many examples as we can, and also we can look at our transcendental functions like the exponential functions as well as the logarithmic functions. And then of course there are also rational functions that are continuous depending on the domain. Now there's a certain type of discontinuity that we have to look at, and in this slide we have the function y is equal to f of x, and if you look at this is not a discontinuous. In other words, f of x is a continuous function. So here we have that this is a continuous function. However, for b and c, these two functions are discontinuous. Okay, it's discontinuous, and then we'll see why. Well, look at this. We use our continuity test. First, what is f of, we're looking at letter B now. What is f of 0? Because that's where where there's a possibility that there is a discontinuity right there. So what is f of 0? Oh, it's not even defined, so it does not exist. Even though the limit of f as x approaches 0 is 1, but since it has no function value there, that's where you have a hole, then the function is not continuous. Okay, how about this one? Well, let's look at f, letter C. What is f of 0? Well, f of 0 is 2. Now, what is the limit of f as x approaches 0, both from the left and from the right? The y values approach 1. The problem is they're not equal to each other. So if we recall our test of continuity, it has to be that the function value exists. Not only that, because here the function value exists, but the limit as x approaches the value, like here at 0, the y values, its limit corresponds to the value of f of x at that point. So that means it just doesn't have any hole. Let's go back here and examine these two functions that are discontinuous. In other words, if we redefine the functions, both b and c, in such a way that f of 0 now, instead of being being the case that it does not exist, we dictate that it's equal to 1. And similarly here, we redefine a new function value at 0 and we say it's equal to 1. Then when that's the case, we can say that the discontinuity has been removed. So these two types of function, b and c, are functions which have removable discontinuities. So what is a removable discontinuity? They both have limits at the point where we're looking at, and if in the case it does not exist, then we just redefine it to be at the limit value. And here it does have a function value, but it does not coincide with the limit value. So we just have to move that dot over there. Then we have removed its discontinuity. Okay, now let's look at these functions where they're all discontinuous, D, E, and F. Here we cannot, these are the types of function where we cannot remove the discontinuity. And why is it the case? Because if we look at D, okay, the limit of F, as x approaches, what's our critical point? It's at 0, right there. Okay, so what's the limit as x approaches 0? We have seen that this does not exist because its two-sided limits do not coincide each other. What about this function? Well, the limit, let's look at E, the limit of f as x approaches 0, coming from the left and from the right. Here, it's not a number, it's plus infinity. Okay, so again, it does not exist. We'd say the limit is at infinity. And we'll talk about that in the next section. Okay, so what about letter F? We have a function. Again, this has been an example that I've shown before. And we said earlier that the limit in letter F, the limit of sine of 1 over x as x approaches 0, whether from the left or from the right, remember that the sine of 1 over x oscillates rapidly back and forth from -1 to 1. Okay, it just bounces. And we will never really zero into a particular point, so the limit does not exist. So whenever you have a case of functions where the limit does not exist, right here, then it's not a removable discontinuity. Get that? Okay. Let's recap. First of all, among these functions from A to F, only A is continuous. All right, and of course, in particular, it's continuous at every point, but we just look at, in particular, at x equal to 0. Okay, but from B to F, all the functions are not. They are not continuous. So this is not continuous, not continuous, not continuous, not continuous, and so on up to F. And we have that B and C have a removable, each has a removable discontinuity because the limit exists right there. The limit exists in these two cases, except here in letter B, the function value does not exist. Here it does exist, but does not coincide with the limit value. So again, there is a remedy. That's why it's called removable. We can remove the discontinuity by redefining the y value at the point x equal to 0 and let it be equal to the limit value. And here, same thing. You just scoot down and move that point and make sure that it would plug up the hole. And of course, from D, F, and E, these are the types of discontinuities that we cannot remove. Why? Because from D to F, okay, the limit of the function does not exist. So whenever you take a look at a function and examine the continuity at a particular point, once the limit does not exist, then there's nothing we can do. We cannot redefine at all.